This is Unit 3, Video 8. In this video we will talk about bond angles formed by the 5 types of molecules, or 5 categories of molecules that we've talked about. Now the bond angle, just to remind you, is based on the circle. So if you have a circle, remember that circle has an angle of 360 degrees. So that's what these bond angles are based on. So for example, the linear geometry, if you have half of a circle, then half a circle obviously will be 180 degrees. Remember, linear is formed when the 2 electron domains go as far as they can from each other, which allows them to orient themselves in opposite directions, which is 180 degrees in terms of geometry. So that one's the easiest one to see. The next one is 120. If you have trigonal planar, which means all 3 go in 3 different directions, you get yourself the circle 360 divided by 3, and that's how you get 120. This one's also pretty simple to see. Now, when you get to the tetrahedral, you don't get what you would expect. If you divide 360 by 4, you would get 90 degrees. You don't get 90 degrees here. You in fact get 109.5. And remember, what happens is with tetrahedral, you don't orient yourself in 2 dimensions, you extend into 3 dimensions. So if you have 4 areas of electrons, for example, if you have CH4, we draw CH4 like this, and it looks on paper like the 4 atoms of hydrogen go in to 4 directions using 90 degrees. It looks like this is 90 degrees, but it is not, because they actually go into 3 dimensions. So one of these hydrogens, for example, would stick out in 3 dimensions towards you, like you're seeing happening here, and your bond angle actually increases to 109.5, so it's greater than 90. Because remember, these orient themselves to try to minimize repulsion, so they go in opposite sides, and that's how you get this bond angle. It is less than 120, but greater than 90. That's a good way of thinking about it. And really, you have to just remember this number. 109.5 is the famous bond angle of tetrahedral geometry, which is exemplified by a lot of molecules. So that's an important angle. That covers the first 3, and then the expanded octets begin with Trigonal Bipyramidal. Here you actually have 2 angles. You have the trigonal angle right in the middle, that's in the plane or in the equatorial position. That looks just like this one. Essentially, it's this one just placed in the middle of the molecule. So that gets you 120. And then the axial positions above and below the molecule would give you 90 degrees. Now that's because we're not measuring the axial positions in terms of each other. We're measuring the axial and the equatorial, which gives us the true 90-degree angle. So in fact, you have 2 possible angles, 90 and 120, and the one you choose will be dependent on the atoms that we talk about. So say if there's an atom here and there's an atom here, and I ask you for the bond angle, you would say 90 degrees. But if I'm asking for these 2 atoms, then you say 120. And as you'll see, if you have electron pairs, sometimes the 120 disappears altogether and you just use the 90. And we'll show you some examples of that. The final geometry, the octahedral geometry, has only 90 degrees, which makes it easy. So in fact, this one's the one that gets you 90, because you have 6 electron domains oriented in 3 dimensions, and that gets you the 90 degrees. Okay, so you'll have to remember these bond angles, but we'll practice to make sure you have enough examples to remember these. Now it turns out these bond angles can be adjusted a little bit by some effects. So the first effect is the non-bonding pair. So if you take a look at something like this, notice you have 3 bonds. In other words, you have 3 hydrogen atoms, and then you have a non-bonding pair or a lone pair up here. Here it says that non-bonding pairs are physically larger. They actually extend out a little bit. So if I were to draw this actually extends out a little bit. That's because this pair of electrons is not shared between 2 atoms like this pair is, and so it can take up more space. It's not constrained as much. And so the repulsion between, or the repulsion due to this lone pair is greater. And this tends to push down on these bond angles and actually push them in a little bit, giving you not 109.5 like we would be used to. We saw this as 109.5, but you get down to 107 if you have 1 lone pair. Now if you have 2 lone pairs, like in the case of water, this is actually very famous, these extend out a little more as well because they are not shared. So they take up more room, you can say, and they push this down to 104.5 degrees. Now I do want you to know about this. You can either remember the numbers, or you can simply say in these molecules the bond angle will be less than 109.5 degrees. I'm alright if you just recognize that it's going to be less than 109.5. Same thing or a similar thing happens with double and triple bonds. Double and triple bonds, because they have more electrons, so remember a double bond like this one is actually 4 electrons, whereas a single bond like this one is only 2 electrons. So a double bond has more electron density, therefore it will be bigger. And what happens is, because it's bigger, so if you were to draw this electron density, you would draw it bigger, these would be drawn smaller. This one does the same thing, it pushes in. And I think I'm kind of drawing over the structure a little bit. Let me clear it so we can see it. The arrows are already there, kind of showing you that the double bond actually creates a larger bond angle of 124.3. This one's 124.3, and remember these begin, trigonal planar begins as 120. If all three of these bonds were equal, it'd be 120. So this one increases by a little bit, and this one actually decreases by quite a bit. Now, you don't have to know exactly the numbers, but you would say, if I were to ask for this bond angle, for example, you could say that's less than 120. If I were to ask for this bond angle, you could say that is greater than 120 degrees. And same thing happens then with double bonds and triple bonds. Okay, so make sure you understand bond angles. We're going to move on to another concept here. This, before we do, let's do a little example of a bigger molecule that has multiple atoms, and you can actually determine the geometry and the angles of every atom. So here you have a big molecule called acetic acid. If you draw its structure, it actually has 3 central atoms. So you can talk about the geometry around each of these central atoms. Now if you take a look, it's lined out right below. Here, this portion of it, if you take a look, we have 4 electron densities, so 4 electron domains, and that gives us 109.5 degrees. Here, in terms of carbon, we have 1, 2, 3 electron domains. By the way, this would be tetrahedral with 4. This would be trigonal planar with 3. Trigonal planar gets you about 120. Now, because you have a double bond here, this double bond actually extends a little more like we've talked, so this will be actually less than 120, a little bit less than 120. And in the case of this last one, oxygen, this is 4 electron domains. Recognize that whenever you want to talk about bond angles, you have to do it in terms of electron domains. You look at electron domain geometry, not molecular geometry, because, well, you could take a look at like molecular geometry, but electron domain still considers these electrons, and that's why we look at it. So it's tetrahedral in terms of electron domain geometry. The molecular geometry here would be bent. Just like with water, it's bent. However, the bond angle is 109.5 because tetrahedral is the electron domain geometry that influences the bond angle. Hopefully that makes sense. And in fact, it will be less than 109.5 because these non-bonding pairs extend out a little bit, creating more repulsion. So you can actually look at big molecules like this and predict the different geometries and the different bond angles. So we're going to do just that with some examples, and then we'll go on to the second concept. So here it says, predict the bond angles around the central atom in these 3 molecules. So let's go and do the first one. I'll quickly draw the Lewis structure, and you can pause and check to make sure that is done correctly. Now, in the case of oxygen and chlorine, what you'll have is you'll have chlorine be in the middle, and then oxygen around the outside. We've kind of seen this with nitrogen, a similar effect with nitrogen, because chlorine is less electronegative than oxygen. And then what you get is you get yourself a total, everyone should have a full octet for a structure that looks like this. And actually, you should have 14 plus 6, a total of 20. So that should do it. Now, if you take a look at the bond angle, it says give the bond angles. We're talking about the bond angle that's right here, between the 2 outside atoms, you can say. Now, this whole molecule is based on a tetrahedral electron domain geometry. So what you've got one in the middle, and then you've got this picture. If you if all 4 of them had atoms, you'd have the regular tetrahedral arrangement. But remember, if 2 of them are electron pairs, so we consider this to be an electron pair and this to be an electron pair, eventually the shape of the molecule will be bent. So the molecule itself is bent. But the bond angle is still influenced by this electron pair out here. So this electron pair still, these 2 pairs rather, still influence the bond angle. So the bond angle should be based on tetrahedral, even though the molecular geometry is bent. And tetrahedral was 109.5. Now, we said that you have lone pairs which extend out, push in a little bit, and these will push essentially these backwards or into it if it's in 3 dimensions, and you get the real answer is less than 109.5 degrees. So this is actually the final answer for our first example. Alright, let's do our second example, O3. I'll have to move O3 out here. Again, let me draw the structure, and you should make sure you can draw these. This actually contains a single and a double bond, which means it will contain resonance. This is famous ozone, which exhibits resonance. Now, this is important because resonance shows us that the 2 electrons are actually the same, or rather the 2 bonds are the same. Oops, another pair here. So this is signifying that these bonds on the left and on the right are equivalent. Now this is based on the electron geometry of 1, 2, 3, so this is based on Trigonal Planar electron domain geometry. And Trigonal Planar has 3 areas of electrons, which means they'll go 3 opposite sides of a circle. You get 120 degrees. Now, here we're essentially measuring this bond angle. You always measure it between the atoms, not the bond, not the lone pair. But because this lone pair creates more repulsion, you can say, takes up more space, again, this bond angle down here will be less than 120 degrees. So this is less than 120. Hopefully that makes sense. This last one, BrCl3, let me create a little bit of room so we can fit this one in. BrCl3 is actually an expanded octet. Get rid of this as well. So the expanded octet, let me draw him. You should get yourself a bromine in the middle, 3 chlorines on the outside, and you should get yourself, everybody should be fully octet ready, and then the bromine in the middle should have 2 extra pairs, because you should have a total of, since each of these brings 7 times 4, you should have a total of 28 electrons, and you got 8 around each on the outside. That's 24, 25, 26, 27, 28, so that should give us 28. Okay, so this is actually based on Trigonal Bipyramidal. So you have 5, 1, 2, 3, 4, 5 electron densities. Remember that Trigonal Bipyramidal has 2 axial atoms and 3 equatorial atoms. They look like this. Now, if 2 of these are non-bonding pairs, here they are, 1 and 2, the non-bonding pairs, remember, go on the equatorial positions. They actually go here. That's because equatorial positions are more expanded, they're further out, and that's why non-bonding pairs taking up more space will go on the less crowded position. So this is your non-bonding pair, this is your non-bonding pair. What you get that's left is actually T-shaped. Now, this T-shape is the area where we will ask for the bond angle. So we're actually asking for this bond angle or this bond angle. They are equivalent in this case. And between the axial and the equatorial position, we said the bond angle is 90 degrees. So that's the answer here. The answer here is 90 degrees. All right, hopefully that will make sense. I will go on to the next concept in the next video. This completes video 8 for us.